Welcome back to this geometry series. Our next topic will be special right triangles. So, as we talked about right triangles in the past, very simple. Right triangles have a 90-degree angle. We symbolize this by this kind of L-shaped kind of bracket there in the corner. That means a right angle or an angle of 90 degrees. Special right triangles are a case of right triangles that have special properties that you don't necessarily need Pythagorean's theorem to solve for. We will use it to prove those values, but the first type of triangle is called a 30, 60, 90 triangle. Basically, all that means is we have three angles of a triangle. Each one of those angles are 30, 60, and 90 degrees. So, what this means, the side length that is opposite the 30 degrees has a side length of x. The side length opposite the 60 degrees has a length of x times the square root of 3, and the hypotenuse, always opposite the 90-degree angle, is going to be 2x. So, quick example with this, if we have a 30, 60, 90-degree triangle, and the side opposite the 60 degrees has a length of 18, so that's opposite the 60-degree angle. What are the other two side lengths? Well, if we look at this 30, 60, 90-degree triangle, the side length opposite 60 has a length of x square root 3. So we can set 18 equal to x square root 3, solve for x. So we'll divide both sides by the square root of 3, and we get that x is equal to 18 over the square root of 3. We can get rid of that square root in the denominator by multiplying by a ratio of 1, or square root 3 over square root 3. And this will be a topic of another video, but the square root 3 times square root 3, that multiplies into 3. And then on top we have 18 square root 3. The 18 and the 3 can simplify, and this just becomes 6 square root 3. So we have our 30, 60, 90 triangle. This is our 30, this is our 60, this is our 90. We're given 18 over here. We've already now solved for the value of x, which, as you can see, is the side length opposite the 30-degree angle, this one down here. So that would be a side length of 6 square root 3. And then the hypotenuse is now just 2x. So we can take this number, multiply by 2, and we get 12 square root 3 as our hypotenuse. So relatively simple. The next type of triangle is a 45, 45, 90. So similar to the 30, 60, 90, this name just denotes that there's two 45-degree angles and one 90-degree angle. Now, as we talked about with isosceles triangles, when you have two angles that are the same in a triangle, that means their opposite sides are also the same. And that means it's an isosceles triangle, it's symmetric down the middle here. So if each one of these legs have a length of x, the hypotenuse then has a length of x square root 2. And we can easily check both of these with Pythagorean's theorem. For the 45, 45, 90 triangle, remember that's leg 1 squared plus leg 2 squared equals hypotenuse squared. So x squared plus x squared equals x square root 2 squared. Obviously this becomes x squared plus x squared, and then over here we have x squared times square root 2 squared, which is just 2. So 2x squared equals 2x squared, and this checks out. For the 30, 60, 90 triangle, it's the same exact process. So we have leg 1 squared plus leg 2, which is x square root 3 squared, and that is supposed to equal the hypotenuse of 2x squared. So once again, we can simplify this out. X squared plus now x square root 3 squared is x times x, and then square root 3 times square root 3. So we have x squared, and then we have a 3. And then over here it's 2 squared and x squared, so 4x squared. We can add both of these guys up. X squared plus 3x squared, that's 4x squared. And that checks out. So we're good. Now, the final type of special right triangle is what we call a Pythagorean triple. And we mentioned this briefly in the previous video. But what this means is using Pythagorean's theorem, we know there's an a, b, and c, and a squared plus b squared equals c squared. This works for any right triangle, no matter what the lengths are, as long as you have a 90-degree angle in this bottom corner. So there are a few select combinations of numbers where you get whole integers as values of a, b, and c. Examples of this are a 3, 4, 5 triangle, which means leg 1 is 3, leg 2 is 4, and the hypotenuse is 5. 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, and then 5 squared is 25, so that checks out. Another really common one is 5, 12, 13. And keep in mind the biggest number is always going to be your hypotenuse, because the hypotenuse is the longest side of any right triangle. Other common ones are 7, 24, 25, and then 8, 15, 17. There are a lot more. You can keep also expanding these out and scaling them up. So for example, 3, 4, 5 is a perfect right triangle on the Pythagorean triple, but so is 6, 8, 10, just 3, 4, 5 times 2. You can do this with any set of Pythagorean triples and any whole number scalar. You can scale these up as many times as you want, and there are actually an infinite number of these Pythagorean triples, but they're good to know. If you ever see a side that has 3, 4, 5, or 5, 12, you know the last hypotenuse is always going to be 13. So that's kind of it for the special right triangles, and I hope to see you in the next video.